So far, as it relates to the different videos that have appeared within this playlist, and as it pertains to the subject matter of the normal distribution, we've been operating under the assumption that the data that we're working with is always perfectly normally distributed. It always adheres to a perfect normal distribution, textbook normal distribution. However, what if it does not? And why does it matter? Well, I hope to discuss that in these slides that we're going to be going through today. And I forgot to mention in some of the other videos, but the code and the CSV files for each one of these lectures can be found in the video description. So make sure you check that out. So many statistical tests require that data be approximately normally distributed. And in most natural settings with samples of scale, you can operate under the assumption that the data is normally distributed or close enough to a normal distribution. So what this means is we need to test our data. If we have data that we're observing from a phenomenon and we're taking down different observational samples, well, we need to test that data. We need to see if the data is close enough to the normal distribution where the same attributes and characteristics of the normal distribution are applicable to our understandings of the phenomenon that we're looking to study. There's instances where this may not be the case, or the data might be close enough to a normal distribution, but in most instances, and actually almost all instances, data is not going to be perfectly normally distributed, but it might be close enough to a normal distribution that we can draw inference and run certain tests operating under that assumption. So approximately normally distributed data is known as parametric data. Parametric data means that the data is close enough to a normal distribution that a lot of the similar characteristics of the normal distribution apply to our data observations and the general phenomenon which we're observing. Non-parametric data means that the data still is somewhat close enough to a normal distribution, but we need to run a different sort of methodology. Not all of the assumptions and characteristics of a normal distribution are applicable to our observation. So remember, perfectly normal distribution, it's only something in a textbook. It's only something in the classroom. It's the perfect instance, the perfect occurrence of something happening. Parametric data means that the data is approximately normally distributed. It means that it's close enough that a lot of the characteristics of the normal distribution as it exists in the textbook, as it exists in the classroom, are also applicable to our data, are also applicable to our phenomenon. Non-parametric data means that the data still somewhat adheres to a normal distribution. Some of the characteristics, more or less, might be applicable. We can draw some inference, but we're not going to be able to use certain tests. We're going to have to use a derivative of the parametric tests that we would otherwise utilize. And what this means will become clearer as we start doing inferential statistics examples. So if we have data and we want to know as to whether or not the data is parametrically distributed, we have to run a bit of tests. All right. Now, some of these tests are better than others. The Shapiro-Wilk normality test, this is the tried and true. If you're operating in the field, really, this is the only test that you need to utilize to determine whether data adheres to a parametric distribution. Okay. A histogram is something that you might use in a classroom to draw this distinction. But as you can probably remember from some of the prior slides, histogram measures frequency, not distribution type. So it's not a perfect one-to-one analysis. You're only going to be able to see the frequency of occurrence from our phenomenon, not the distribution type. Mean and median, again, is something that you'll utilize should Shapiro-Wilk not be available. And skewness assessment and kurtosis assessment also are tests which are a bit off the beaten path that you can utilize, but in most instances, you'll want to use a Shapiro-Wilk normality test, and that ought to be enough to put whatever it is that you're researching to rest as to whether it's parametric or otherwise. And you can also pair that with a histogram in some cases, but really this is all you need. but use these other tests if you're informed to or instructed by your instructor to use them in addition or independent of the Shapiro-Wilk. So here is how we would run a Shapiro-Wilk normality test in RCommander. So I've already got my RCommander up and ready to go. I've got the data set, which is in CSV format within the video description, already imported. If you needed help with that, there's a video on RCommander utilization and importing data into RCommander that you can watch. That'll help you go through those prerequisite steps. But here is the data set. It's the familiar data set that we've been using thus far. Here it is. And I clicked on View Dataset to view it. It's already imported as dataset. And what we're really going to concern ourselves with is variable B here. So variable B is the variable within the dataset that we're going to be testing for distribution type. And we're concerned if the data is parametrically distributed. So let me get out of this. So what we're going to do is we're going to go to Summaries within the Statistics option. And then from this menu, the submenu, we're going to choose Test of Normality. Now we're only interested in variable B, so we'll select variable B. And if you have a different data set for your class, select whatever variable you're interested in. But we're interested in variable B. In this case, variable B is a continuous variable. The normality test that we're going to run is the Shapiro-Wilk. These other tests don't even bother. Just Shapiro-Wilk, okay? Okay. And then our output that we'll receive in the RStudio console will resemble what is below in this portion of the slide. Now, we haven't gone over hypothesis tests just yet, but we will in later lectures. But the Shapiro-Wilk normality test allows us to establish this hypothesis here. The null hypothesis is the data does follow a normal distribution. The alternative is the data does not follow a normal distribution. Now, if we're operating under an alpha value of 0.05, if our p-value is less than 0.05, we'll reject the null hypothesis. So if our p-value is less than 0.05, we would say that the data does not follow a normal distribution. If our p-value is greater than 0.05, we would say that the data does follow a normal distribution. In this case, the p-value is greater than 0.05. The p-value is greater than 0.05. So we would operate under the assumption that the data does follow a normal distribution. Greater than 0.05, the data does follow a normal distribution. If this p-value is less than 0.05, we would say the data does not follow a normal distribution. And we'll get into hypothesis testing in a later batch of slides, a later lecture. But as it relates to this particular lecture, as it relates to testing for parametric assumptions, if the p-value is less than 0.05, if it's less than 0.05, we would say that the data does not follow a normal distribution. If it's greater than 0.05, we'll say the data does follow a normal distribution. And why that is, we'll get into it later. So if we're operating in the field outside the classroom, that's enough. We have enough, although it's rather close. We would state our findings in the appropriate APA format. We'll get into that later. And we would then operate under the assumption that the data is normally distributed, at least based on the assumptions and the output of this particular test. And then we could apply the appropriate parametric methodologies. Now, if we wanted to take it a step further and run a histogram or create a histogram by running some code in RCommander, this is how that would be accomplished. We'd go to RCommander, Graphs, Histogram. we would choose the appropriate variable. And again, these are all corresponding variables within our data set. In this case, we're interested only in variable B. We will click OK after selecting variable B. And we would then assess as to whether or not the data is bell-shaped. So ideally, if we're trying to make this assessment, we would like to see all of our data, the frequency displayed within the histogram. We'd like to see our observational data resemble a bell. Now, we already performed the Shapiro-Wilk, so we know that the data, based on the assumptions and the outcome of that test, is normally distributed. However, we look at this, we see that this data really is not looking all that great for this particular histogram. We see that there's a potential skew. So this looks like it would be a left skew, because remember, bump on the right, left skew. So it looks like we have a lot of our observation frequency on the right. So that might be, if we were to actually draw out the distribution, we might expect to find a left skew. But ideally, if our data was normally distributed, or from a bird's eye perspective, we were trying to make that assumption based just on the histogram information, we would hope that all of our observations for the histogram would fall into a pattern which is bell-shaped. Now, if we want to do some additional tests as it relates to skewness and kurtosis, we would first need to get the package moments. We'd have to download and install the package moments. We can do that in RStudio. Instead of installing RCommander, you would install the moments package, and you would do that from the appropriate tab in the right-hand corner. And with that package downloaded and initiated, we would then run this bit of code here. These functions, kurtosis and skewness, are functions which are found within the moments package. And that is kurtosis, open parentheses, the name of the data set. I called it DatasetB, $, and then the variable. So in this case, our data set is going to be DatasetB, $, and variable B is what we're interested as far as variables are concerned within the data set, close parentheses. That'll give us the value for skewness if we were to run this code. We can either run it from RCommander, we can either highlight it here and hit submit, or we could just run it in the R console, and it would provide us with the appropriate kurtosis and the appropriate skewness output. And this is what is going on here. And this would be our output. Now, in a perfectly normal distribution, the mean would be equal to the median. You don't need to download the moments package to run this particular bit of code. Mean and median, there's code within R, which is native to this particular function. You just use the function mean, the name of the data set, $, the variable within the data set that you'd like to analyze, median, data set, $, name of the variable which you'd like to apply the methodology. And this is the output. In a perfectly normal distribution, the mean should be equal to the median. In this case, as you can see, there's some differentiation here, but in the perfect world, these values would be pretty close to one another. As far as kurtosis is concerned, if the data is normally distributed, we would expect to find a kurtosis value between -2 and +2. In this case, the kurtosis value is 1.59, so it falls in between the two, thus indicating, if we're considering kurtosis, that the data is close enough to a normal distribution to meet parametric assumptions. And for skewness, we're also looking between -2 and +2. In this case, our skewness is -0.195, so right around the 0 mark there. So it's close enough to the normal distribution that we would assume that the parametric assumptions are made. So let's consider all of the evidence. I'm sure you've heard of it. Quacks like a duck, acts like a duck, walks like a duck. It's probably a duck. Well, it's true for our analysis as well. In this case, we looked at Shapiro-Wilk. We found it to be convincing. The histogram may possess a skew, but we're not really looking at the distribution type. We're looking at the frequency. So, I mean, that's good. We'd prefer it to be bell-shaped, but it wasn't, but maybe close enough. Median and mean should be close to equal. There was a bit of a differentiation there. However, it wasn't all that vast, I suppose. And their kurtosis and skewness, as far as the eyeball method for those two particular assessments, we had that met in both instances. So we would operate then under the assumption that the data is parametrically distributed. And I just want to, before going to the final slide, just sort of show you what this looks like in RStudio. So let me just get this here. So I've already read in the data set. So here is our moments package. All right, I've already have it initiated. And you can either do that by running this code here, or you could do it by clicking on the box next to moments in the packages tab. If you need to install moments, you would click install and then type moments in the menu box and then install, and then moments would install for you. And then, of course, you'd have to find it in the packages and click the box next to it to get it working, or type library moments up here. Here is the mean function, the median function, which are native within R. And here is kurtosis and skewness, which you need the moments package to execute. So if you were interested in doing this yourself, whether it be in RCommander, if you were doing this in RCommander, you would just have this code in your RCommander box over here, and you'd submit it and it would work. Or you could do it directly from RStudio, whatever you'd prefer. So let's state our findings. The distribution of the sample is not significantly different from a normal distribution as assessed by the Shapiro-Wilk test. There's our p-value from that test. The skewness of the sample was found to be negative 0.20, and the kurtosis was found to be 1.60. And here is our histogram. So this statement, as far as the distribution of the sample, is not significantly different from a normal distribution as assessed by the Shapiro-Wilk test, p equals 0.07. We'll go into what p-value is indicating, how to select an alpha value, etc., in future lectures. But just know how to operate the Shapiro-Wilk and how to structure the hypothesis and what the p-value is indicating given an alpha value of 0.05. Just know that for this particular batch of slides, this particular lecture, just know it generally, and we'll go into more specifics as we continue on through this playlist. If you made it this far, congratulations. We're really getting into it now. We're really going to be getting into analysis, applicability of methodology, and things that should help you as a researcher throughout your research career. So with that, if this was helpful, please consider liking and subscribing. It would mean a lot. Again, code is in the video description. I thank you for spending this time with me, and I hope that you have a wonderful rest of the day. Take care.